Alright, so next I will discuss about a very important but extremely counterintuitive topic in the quantum physics. It's called the collapse of the wave function. And this topic is very much related to the experimental versus theoretical interpretation of the quantum physics. In fact, the foundation of the quantum mechanics started from some of the very puzzling experimental outcome, which people have spent a long time to come up with a theory which can explain those outcomes of the experimental observation. So in quantum mechanics, the observation and the theoretical interpretation needs to be understood very carefully, because the act of measurement or the act of observation for any given quantum mechanical problem can actually lead to a very different result. So understanding this particular aspect is very important. So and it is related with something called the collapse of wave function, which is from the theoretical interpretation of it. So in order to understand this particular topic, let me brush up few of the topics which probably have already been taught to you previously, but I'll just quickly brush it up so that we are on the same page. So we have actually learned about infinite potential well problem, which is shown in the right cartoon diagram here. And we after solving this problem, a particle inside this potential well, after solving this problem, what we found, basically solving the Schrodinger equation for this problem, what we found is that this particular particle inside this potential well can only take discrete set of energies, which in other words is also called the energy is quantized in this potential well. And also it can have specific wave functions corresponding to those discrete energy values. And for a particle in this rigid box, the nth wave function is shown by this expression psi n equal to root 2 over L sine n pi x by L, where L is the width of this potential well. N is an integer which goes as 1, 2, 3, 4, 5, so on, not 0. So if I consider another wave function psi m, which is denoted by another integer m, then one can actually prove that the integration of the product of these two wave functions psi m star and psi n is always 0 if m is not equal to n, and this particular relation is called the orthogonality relation. However, if m is equal to n, then this integration 0 to L psi m star psi n is 1, and this is also called the normalization condition. So this is how the general relation look like. Integration 0 to L psi m star psi n dx is delta mn, where delta mn is also called Kronecker delta function, which takes value 1 if m is equal to n and is 0 if m not equal to n. So when m is equal to n, this actually gives rise to the normalization condition, as you might have learnt already. So in general, this is not only true for this particular problem in the infinite potential well, but in general for any given wave function psi n and psi m, this is true for any given wave function and operator in quantum mechanical problem. There are a few other very important properties of these wave functions, and in fact an acceptable function fx that is 0 outside this region of the potential well, that is x equal to 0 and L, it can actually be written as a linear combination of these wave functions psi and x, and this is also called the completeness relation. So I can write any well behaved acceptable function f of x as a linear combination of my eigen function of this particular problem. And once again, this is true for any eigenfunction of a given quantum mechanical problem, where the Cn's are the constants, and it has very important interpretation. Cn in fact can be calculated by this particular expression, which you can easily derive by using the orthonormality condition. Okay. All right. Now there are a few other properties we'll discuss. It's called superposition and related effects. So what is the superposition of a wave function? The superposition is basically a property which any particle in a given potential well has before you actually measure the system. So in the case of, for example, potential, the infinite potential well, as we discussed, that the particle has various wave functions, psi 1, psi 2, psi 3 and so on. Before I do a measurement to find the particle where and in which energy state the particle is, the particle actually remains in a mixed state or in a superposed state. So this is what I have written here. The wave function remains as a linear combination of psi n, and in fact if you take into account the time dependence, then there is a factor of e to the minus I nt by h cross which also comes in. And this particular wave function apparently also satisfies the time dependent Schrodinger equation given by this expression I h cross d psi dt equal to Hamiltonian times psi. So if you just operate h on psi and take the derivative d dt, you will see that this wave function psi actually satisfies this equation. Okay. What are the interpretation of these coefficients Cn? Here this mod Cn square is the probability of getting the energy En as a result of the energy measurement. And if you enforce the normalization condition, then one can show that sum over n mod Cn square is equal to 1. So with different n values, mod Cn square basically gives the probability of getting the nth energy values. So if a particle, before I measure it, if it exists in a given linear combination with the coefficient Cn, then the probability of finding the particle in the nth energy state is mod Cn square. This is the physical interpretation of this coefficient Cn. Notice that the possible energy values are again not continuous. It can only take discrete values. All right. So infinite potential well, again, let us look at a very simple example of superposition of waves. Suppose I have a particle in this potential well which I have not measured it, and it actually exists as a superposition of two waves, the psi 1, the ground state, and psi 4, which is the third excited state. So suppose that the particle exists in this particular infinite potential well as a superposition of these two wave functions, which means I can write the total wave function psi x0 as a linear combination of psi 1 and psi 4. So root 2 by L sine pi x by L and root 2 by L sine 4 pi x by L. Now the question is, when I superpose different wave functions to form a general superposed wave function, it may not always be normalized. For example, the first equation here, psi x0 equal to root 2 by L sine pi x by L plus root 2 by L sine 4 pi x by L, this particular wave function is actually not normalized, and the reason being, if you take integration psi star psi dx, it is not equal to 1. So you can actually evaluate this integration which I have written here. So this is apparently not a normalized wave function, but you know that we always have to work with a normalized wave function, which is a better way to proceed. So what we can do is we can normalize this wave function, and if I take into account the correct normalization factor, then a properly normalized wave function looks like this. So you need to divide by 1 over root 2 in order to make this wave function normalized, such that integration psi star psi dx is equal to 1. All right, great. So we have formed a superposed or a mixed wave function, a normalized mixed wave function, which is a combination of the ground state and the third excited state wave function. All right, what's the purpose of doing this? All right, so the way we physically interpret is this, that in this particular form of the wave function, the physical interpretation implies that if I consider a large number of such infinite potential boxes where the wave function of the particle is given by this psi x0, and if a measurement of energy is done on this particular state of the particle, then in half of them we will find the particle to be in n equal to 1, and in the other half we will find it n equal to 4. Why is that? The reason being, if I go back, if I go back here, you can see that the last equation is summation over Cn squared is equal to 1 plus 1 equal to 2. That means there are two Cn, there are two coefficients here which connects or which superpose these two wave functions, and each of them has 50% of the probability. Mod Cn square, mod C1 square is 1, so as mod C4 square, which means it has 50-50 probability of finding the particle in the two states. So if the physical interpretation is that if I take a large number of such infinite potential box, exact same copy of these boxes where the particle exists in this superposed state, and if I do a measurement on each of them, you will see that in almost 50% of them you will, once you do the measurement, in almost 50% of them you will find the particle in the ground state, which is n equal to 1 state, and in the other 50% you will find the particle in the n equal to 4th state. And this 50% probability will be close to 50% if you have larger and larger number of boxes. So because this is a statistical property, you know, the larger the number of such copies of infinite potential box, the more accurate are the probabilistic values, which are 50% for n equal to 1 and 50% for n equal to 4. All right, great. Now let us ask few questions. Let us now construct another wave function which is given by this expression. The first question I will ask is, so the thumb rule is, if I am given a linear combination of different wave functions to form a given superposed wave function, the first question I will ask is whether it is normalized or not. Okay, so in order to check whether it is normalized or not, I will just take the integration of psi star psi, set it equal to 1, and then calculate the normalization constant, the usual procedure. And it turns out that a normalized wave function looks something like this: root 1 by 5 psi 1x plus root 4 by 5 psi 4x. Now it is normalized because the Cn, the C1 here is root 1 over 5 and C4 here is root 4 over 5, and if I sum it up, mod C1 square plus mod C4 square, I'll get a 1. So definitely now this psi x0 is a normalized wave function, and you can easily understand that if I do a measurement, the probability of finding this particle in the ground state is 1 over 5, which is 20%. However, the probability of finding this particle in the n equal to 4 state is 80%. It is basically 4 by 5 into 100. So depending on how I linearly combine different wave functions, it can have different probability of finding it in a given state if a measurement is done. So in the previous example, it was 50-50% probability. In this particular example, it is 20% and 80% for n equal to 1 and n equal to 4 state. What is the expectation value of the energy? So if I quickly calculate the expectation value, which is nothing but expectation value psi h psi, you will see that it will come out to be something like 0.2 E1 plus 0.8 E4, something which can be easily solved, and I think you should do it yourself, but I just wrote the final answer here. The C1 square and C4 square are coming from the previous slide because we have already calculated that. So the expectation value of the energy is 0.2 E1 plus 0.8 E4. So it is a mixture of two energies. We can also talk about the time dependence in these. See, so far we have been talking about the time independent wave functions at time t equal to 0. But what if I want to see as the time goes how these wave functions evolve? So we can actually write a time dependent wave function which I have written here, psi xt is equal to this. It's just that in both these terms I will have to include a exponential minus e n t by h cross term. So you can see in the first term it is exponential minus I e1 t by h cross. In the second term it is exponential minus I e4 t by h cross. And we can actually check that this is a non-stationary state, and the probability of finding the particle at a location would actually be a function of time because of exponential minus I t by h cross term. So this is a state of indefinite energy. There is no definite energy to this state at time t. Okay. Now we can actually calculate the uncertainty in the energy here, which means I can calculate the expectation value of energy E, which is, as I said in the previous two slides, is 0.2 E1 plus 0.8 E4. One can also calculate the expectation value of E squared, which is 0.2 E1 squared plus 0.8 E4 square. And if you calculate the uncertainty in the energy, you will see that it is 0.4 E4 minus E1. And which means that there is a finite uncertainty with respect to the energy of this state. So as I said in the previous slide, the energy of this time dependent wave function is not definite, rather it is having some uncertainty in it. Now this is a very important slide, act of measurement. When I have a mixed state at a given time t and I do a measurement on this, what does happen? So the question that I will pose is, if a measurement is done in one of the boxes at t equal to 0. So I suppose I again have a large number of such same copy of boxes, and I do a measurement one of these boxes at t equal to 0, and suppose the energy is found to be E4. The question is, what would be the wave function at a later time t? Okay, in that particular box where I did the measurement, where I found the energy to be E4, what will be the wave function at a later time t? So the answer to this question is that the wave function, as soon as I measure it in one of the box and I found the particle in a given energy state, say E4, the wave function very quickly collapses and the time dependence would be given by this particular expression. So it, as soon as I measure it in whatever linear combination of the different wave function it was before the measurement, after I did the measurement, it actually collapses to the same energy state for which I got the energy. So in this case it is E4. That's why the wave function now collapses to this particular wave function, which is root 2 by L sine 4 pi x by L e to the minus I e4 t by h cross. Now an important thing to note here is that the normalization constant now has changed. Previously it was something else. I think it was root 4 by 5, however now it is root 2 by L. So this particular wave function is definitely normalized, and it is actually a collapsed wave function after the act of measurement in the energy state E4. Next question, which is again very important, is what will be the outcome if I measure again at a later point of time t? So what would be the measurement of energy yield on this box at a later time t? So it is the same box which I have initially measured where the energy state came out to be E4, Now what I am saying is that I waited for some time and did a measurement of the energy again in that particular box. So the answer in this case will be the particle is now in a stationary state. As soon as I measure it and I found that the particle was in energy state E4, the particle now becomes into the stationary state, and hence the measurement would lead to E4 again. And in fact, in the absence of any external effects, if I don't disturb the system or if I don't perturb the system after my first act of measurement, the result will remain the same, which is E4 at any later point of time and for any observer. So if I don't disturb the system or perturb the system too much, it will remain in that. However, if I disturb the system a little bit and then I do a measurement again at a later point of time, it can be found to be in a different energy state. Okay, so what happened basically? How does the probability densities before and after the collapse changes? So before measurement, my wave function was psi xt equal to a linear combination of ground state and the third excited state. After the measurement, my wave function changes and it became purely the n equal to 4 state. So in state 1, the probability density oscillates with frequency omega equal to E4 minus E1 by h cross, because it has both the energy E1 and E4 in its wave function. So in state 1 it oscillates with a certain frequency, and there is some radiation which comes out because particle oscillates in this case. However, in state 2, when I already made a measurement, the probability density remains the same with time and particle is stationary, so no radiation happens. So it becomes a stationary state after I make the measurements. Okay, moving on. So in short, the effect of measurement is like this. Initially, for a general wave function, before I do the measurements, my particle actually remains in a linear combination of all the states, so which is written as a summation over all n psi n xt. As soon as I measure it, it gets collapsed into the nth, a given nth state psi n xt. So to be more precise, quantum state is extremely fragile. Before I do the measurements, the measurement causes the wave function to collapse abruptly and non-deterministically. So the word non-deterministically is extremely important. If the wave function is the eigenfunction of the operator corresponding to this measurement, then the result will be one of the eigenvalues. Otherwise, if it is not, then the result will be some value, not the expectation value. So if I want to just quickly show a pictorial diagram for such effects, collapse of wave function. So before measurements, I have a wave function which is in superposed state, and you can see it is like a blob, right? As soon as I do this measurement, this blob, this very largely spread superposed wave function collapses to a particular place like this on the right hand side, and it just became a given stationary state like psi 4 in the previous case. Okay, so there are again real time example of such collapse of wave function, and I really would like to go back to the double slit experiment, which I'm sure you have been introduced. Remember, in a double slit experiment, when I had two slits and when the electrons were passing through these two slits, you were always getting a interference pattern at the other side. Now the puzzling behavior or the question was, if I consider electrons to be particles, then there is no way particles passing through the two slits will form an interference pattern like this. It is only the wave property of electrons which can give rise to such a interference pattern. However, the more puzzling outcome was when I try to be smart and try to observe how these electrons are passing through these two slits, which means I placed a small detector near the two slits such that as soon as the electron passes through the slits, this detector is such that it blinks, which will ensure the experimentalist that okay, now the electron has just passed. But as soon as I try to measure that, whether the electron has passed through this slit, through one slit or the other slit, the interference pattern actually changes and it became a bimodal distribution. This is actually because of the collapse of the wave function, and it is the collapse of the superposed state. So before I made the measurement, before I put the detector near the slit, the wave function due to the electrons which is coming and passing through the slit were in a superposed state. And as soon as I put an additional detector near the slit, the superposed state now collapsed into a given state. So to be precise, it is the collapse of the superposed state during the detection behind the slit that kills the occurrence of the interference pattern, and it actually because it collapses the wave function, so it transforms into a bimodal kind of distribution, which is actually a particle property. So in fact, there is another very important phenomena in quantum mechanics, which is again counterintuitive as compared to the classical physics, and this is basically related to the order of measurements. Whether I measure one property first or the other property, my outcome can be completely different, and this actually arises because of something called the commutation relation of these operators, because in quantum mechanics we actually talk about operators, and the corresponding physical quantity or rather the observable corresponding to that operator comes from the eigenvalue of that operator, right? So if we make a measurement of two different observables in succession, the result depend on the order of the two measurements. Whether I measure the first property first and the second property later on, or the other way around, my outcome of the experiment will be completely different. And this is because of this mathematical relation. In general, in quantum mechanics, if I have two operators A and B which operate on the wave function psi, if I look at the left hand side, which is like A operator times B operator times psi, which means I am first making a measurement of the observable corresponding to the operator B, and then I make the measurement corresponding to the operator A. However, on the right hand side, it is the other way around. I first made a measurement for the observable corresponding to the operator A, because A is operating on psi first, and then I am making the measurement for the observables corresponding to operator B. In principle, these two order of measurement, or these quantities A B psi and B A psi, is not necessarily the same. The classical example is x operator and the momentum px operator, and in fact these two operators do not commute, which means x times px operator is not equal to px times x operator. So which means that if I have a system with a given wave function, if I measure the momentum on that state first and then the position, the outcome of the momentum and position can be completely different if I measure the position corresponding to that wave function first and then the momentum, because x px acting on the wave function psi is not equal to px times x operator acting on psi. So unlike classical physics, in quantum mechanics the order of measurements makes a big difference depending on what you measure first for a given quantum mechanical problem. I'll stop here and we'll talk about some other interesting topic about the degeneracies in the next class. Thank you.